In this video we'll do a very famous problem. This problem involves a volume of water per second from an open-ended tank through an opening 2 centimeters in diameter that's 5 meters below the water level. And they want to know how much water is going to flow out each second. That is, they want to know the flux. It turns out that this problem was done by Dr. Torricelli, and so it's often called a Torricelli problem. And if you know that, you probably know the formula and can jump to the end. It comes from Bernoulli's equation, in which what's happening here is gravitational potential energy is being converted over into kinetic energy. With the hole on one side, there is atmospheric pressure here. The top of the tank is open-ended, so the pressure at this point is also P naught. So we're looking at this point as point 1, and this point here at the hole as point 2. Bernoulli's equation says that the pressure at 1 plus 1/2 times the density times the volume at point 1 squared plus the density times G times Y1 has to equal the pressure at 2 plus 1/2 times the density times the speed at point 2 squared plus the density times G times Y2. And remind you that this is Y2 and this is Y1, and the difference between those two things, Y1 and Y2, is 5 meters. Now, the pressure is the same at both places. So this pressure here can cancel that pressure there. They're both P naught. And furthermore, up here at V1 is basically 0 meters per second. The water's just lazying around up there. So there's no kinetic energy of that, at least not macroscopically. This still leaves the kinetic energy that the water's going to have when it flows out here, whatever gravitational potential energy it has with respect to the ground. Now we could very easily make Y2 0, and that would make Y1 5, or we can just subtract these two, because the 0 point value of gravitational potential energy is just an arbitrary reference point. So let's write our equation 1/2 rho V2 squared, and I'm going to move this over so I get rho G Y1 minus Y2. Now the density is in both sides of the equation, so we can cancel that. And we can solve for V. And if we do that, the speed exiting this is simply the square root of 2g y1 minus y2. That's just the square root of 2gh, the same answer you get for a falling body. Well, of course it is, because we get that not just from kinematics, but we got that when we did conservation of energy. And that's what we've assumed here, since we've had a non-viscous fluid, and we've assumed that all this potential energy has been converted to kinetic just as if it fell downhill. Now they wanted not that, but they wanted the flux. So to find the flux, we've got to take this speed here and multiply by the area of that hole. So I remind you that flux, which is the amount of water, that is the volume divided by time, is equal to the velocity at 2 times the area at 2. So that's the square root of 2g y1 minus y2, which is 5 meters, times pi times d over 2 squared, where d is the diameter. We now need to put in our values for this. So our flux is the square root of 2 times 9.8 meters per second squared times 5 meters. We have pi, and then to be consistent throughout this, we need to choose some units that are corresponding. This is meters squared per second squared, so that's going to give us a meters per second. So we got a meters per second. We're going to need this in meters as well. So our diameter up here said 2 centimeters, so that's 0.02 meters. So we put 0.02 meters over 2, and we square that. And let's see what we get for a flux. So take my calculator, and I have the square root of 2 times 9.8 times 5. Then we multiply that by pi, multiply that by 0.01 squared, and I get, if I've done this right, now let's see, did I see that correctly? Was it 2 centimeters? Yes, it said it was 2 centimeters. So this is 0.0020 0.0020 meters cubed per second. Now, if you want to convert that to centimeters cubed, which would be milliliters, you would need to multiply that by million. So it's 0.0020 meters cubed per second. But if we multiply that by a million, we get 2,000 centimeters cubed per second, or 2,000 milliliters per second, which means 2 liters per second. This is probably how we would prefer to describe it. So basically a 2-liter bottle comes out of that thing every second. Alright, see you in another video.